Press your hand flat against a table. It feels solid, cool, completely there, and it holds your weight without giving an inch. Yet almost all of that table is empty space, and the specks of matter that fill the rest are built from a few tiny pieces that, when you follow them down far enough, physics can no longer fully explain. That is where we're going tonight, beneath the atom, into the hidden layer where the rules of the universe are written, and where some of those rules trail off into question marks. I'm going to take this slowly, one simple step at a time, starting from the solid table under your hand and working downward. If you enjoy taking your time with big ideas, take a moment to subscribe and we will keep going. The question we're chasing is easy to ask. What is everything actually made of all the way down? The table held your hand a moment ago and it pushed back. That pushing back is the thing we trust most about the solid world. A chair takes your weight, a wall stops your knuckles, a stone, kicked hard, hurts your foot rather than letting it through. From the time you were small, you learned the world by its resistance, by the way matter refuses to share its space with you. Solidity feels like the plainest fact there is, the flaw under every other fact. So it is worth sitting with what that solidity actually is. When you press the table, the atoms in your skin come close to the atoms in the wood, and they push apart. The push you feel is not two surfaces meeting like bricks. It is the outer parts of atoms repelling the outer parts of other atoms, an electric standoff happening across a gap far too small to see. You never quite touch the table. You hover a hair's breadth above it, held up by force rather than by contact. The cool, smooth, unbroken feeling under your palm is your nerves reading that force and reporting back the word solid. The Greeks were the first we know of to ask how far down this goes. Around 2,400 years ago, a thinker named Democritus imagined cutting a piece of matter in half, then in half again and again, and wondered whether you could do that forever. He decided you could not. At some point you would reach a piece that could not be divided any further, and he called that piece the atom, from a word meaning uncuttable. It was a guess, not an experiment, but it was a good guess about the shape of the question. Either matter goes down forever, smaller and smaller without end, or it bottoms out somewhere in pieces that cannot be split. For more than 2,000 years that stayed a matter of opinion. Then chemistry gave it weight. In the early 1800s, an English schoolteacher named John Dalton noticed that elements combine in clean, whole number ratios, 2 parts of this to 1 part of that, never ragged fractions. The simplest way to explain those tidy ratios was to say each element is made of identical little units that join in fixed counts. Dalton brought Democritus back, now grounded in the weights of real substances on a real balance. The atom became less a philosopher's wager and more a working tool. By the late 1800s, the atom had become the bedrock of chemistry, the smallest grain of an element, the thing you could not break without ceasing to have the element at all. Hydrogen was made of hydrogen atoms, gold of gold atoms, and each kind sat in its place on the growing periodic table that Dmitri Mendeleev had arranged. The word still carried its old meaning, uncuttable, and most scientists took that meaning seriously. The atom was the end of the line, the final brick, the smallest thing. That is the picture you inherit, mostly without being told. The world is made of stuff. The stuff is made of atoms, and the atoms are tiny solid balls, the smallest pieces packed together to make everything you can touch. It is a clean picture, and for a long time it held. Hold on to it for now, because it is the honest starting place, the view from the top of the stairs before we begin walking down. The trouble is that the atom is not the end of the line, and it is not solid, and it is not uncuttable. Within a few short years at the turn of the 20th century, a handful of careful experiments would crack it open and show that the smallest brick was mostly empty space with almost nothing inside. That cracking open is where the long descent begins, and it starts with a thin sheet of gold. Around 1909, in a laboratory in Manchester, a New Zealander named Ernest Rutherford set 2 young researchers a careful task. Hans Geiger and Ernest Marsden were to fire tiny charged bullets at a sheet of gold and watch where they went. The bullets were alpha particles, small, fast, positively charged fragments thrown out by radioactive material. The gold was hammered into a foil only a few thousand atoms thick, thin enough to be nearly transparent. Around the foil sat a screen that gave a faint flash of light each time an alpha particle struck it. In a darkened room, hour after hour, the two men counted those flashes by eye. Everyone expected the alpha particles to punch straight through. The accepted picture of the atom at the time was a soft, spread-out blob of positive charge with a negative electron scattered through it like seeds, a model often described as plum pudding. If that were right, the atom had nothing hard in it. The positive charge was smeared thin across the whole volume, far too diffuse to turn a fast, heavy alpha particle aside. The bullets should sail through the gold the way a stone sails through fog, barely nudged. Most of them did exactly that. They passed through almost undisturbed, just as everyone predicted, and for a while the experiment looked like a confirmation of the gentle, spread-out atom. Then Marsden noticed something that should not have happened. A few of the alpha particles, a tiny fraction, came back. They bounced off the foil and flew back toward the source, as if they had hit something solid and immovable hidden inside the near-empty gold. Rutherford never forgot how strange that was. He later said it was about as believable as firing a heavy shell at a sheet of tissue paper and having it bounce back and hit you. A spread-out smear of charge could never do that. To turn a fast alpha particle completely around, something in the atom had to be small, hard, and carry a powerful concentrated charge, all packed into a vanishingly tiny region. The bounce-backs were rare because that hard core was rare to hit. Most bullets missed it entirely and sailed through the emptiness around it. From the pattern of those rare deflections, Rutherford worked out a new picture of the atom, and he published it in 1911. Nearly all the atom's mass and all of its positive charge sat in a minute central lump he called the nucleus. The electrons moved somewhere in the vast space around it, and that space was vast. If you grew an atom to the size of a great cathedral, the nucleus at its centre would be smaller than a fly hanging in the middle of the air under the dome. Everything else, the whole towering volume, would be empty. Sit with that for a moment, because it changes what your hand on the table really means. The table is made of atoms, and each atom is almost entirely nothing. The solid wood, the cool surface, the weight it holds, all of it is built from things that are overwhelmingly empty space. The solidity you feel is not packed matter. It is the electric force reaching across all that emptiness, holding one near-empty atom away from the next. So the uncuttable brick turned out to have an inside, and most of that inside was vacancy. The hardness, the mass, the charge, all of it had retreated into a speck at the centre far smaller than the atom around it. That speck would take decades to understand, and it would turn out to have an inside of its own. But before Rutherford ever found his nucleus, someone had already pulled the first real piece out of the atom, a piece thousands of times lighter than anything else, and that discovery is where the cracking truly began. Step back about a dozen years, to a laboratory in Cambridge in 1897. A physicist named Joseph John Thomson, known to nearly everyone as JJ, was studying a strange glow. If you took a sealed glass tube, pumped most of the air out, and ran a high voltage across two metal plates inside it, a faint ray travelled from the negative plate to the positive one. These were called cathode rays, after the negative plate, the cathode. Nobody was sure what they were. Some thought they were a kind of light. Others thought they were tiny charged particles. The argument had run for years without settling. Thomson decided to pin the rays down by pushing on them. He sent them through electric and magnetic fields and watched how far they bent. A beam of pure light would ignore an electric field. These rays did not ignore it. They swung aside, and the direction of the swing showed they carried negative charge. By measuring how sharply they bent under a known push, Thomson could work out a single revealing number, the ratio of the particle's charge to its mass. That ratio came out enormous, far larger than for any known atom or ion. There were two ways to read that large number. Either these particles carried a huge charge, or they had a tiny mass. Thomson followed the evidence and concluded the mass was tiny, almost unbelievably so. Whatever made up the cathode ray was around 2,000 times lighter than a hydrogen atom, the lightest atom known. And the same particle appeared no matter what metal he used for the cathode, or what trace of gas remained in the tube. It was not a feature of one element, it was something common to all matter, a single kind of piece that every atom seemed to contain. This was the moment the uncuttable atom lost its name in fact, if not yet in word. Thomson had pulled a piece out of the atom, a piece far smaller and lighter than the atom itself. He called these particles corpuscles at first. The name that stuck came from elsewhere, the electron. The atom had an inside, and here was its first identified resident, the carrier of negative charge, light enough that thousands of them together would still weigh almost nothing. Thomson knew an atom is normally neutral, with no overall charge. If he had removed something negative, then something positive had to remain behind to balance it. He pictured the atom as a sphere of positive charge with the small negative electrons embedded throughout, like seeds in a soft fruit. This is the plum pudding model, the very picture Rutherford's gold foil would overturn a decade later. The positive part was spread out and soft, the electron sprinkled within it. Thomson had the electron right, and that part has lasted to this day. The electron remains, as far as anyone has ever measured, a true fundamental particle with no smaller pieces inside it, one of the genuine bottom floor objects of nature. What he had wrong was where the rest of the atom's substance lived. He thought it was spread thin throughout the whole sphere. Rutherford's bouncing alpha particles would soon show it was crushed into a central speck instead. So by the early years of the 20th century, the picture had two firm pieces. There was a light negative electron found by Thomson, and a small, heavy positive nucleus found by Rutherford. The atom was a tiny dense centre surrounded by a swarm of light electrons in a great deal of empty space. The next question was the obvious one. That heavy central speck held nearly all the mass and all the positive charge. What exactly was it made of? The nucleus is the hardest thing in this whole story to picture honestly, because it is small in a way that ordinary words almost refuse to carry. We already shrank the atom down to a cathedral with a fly at its centre. Now we go inside the fly. A typical atomic nucleus is about 100,000 times smaller across than the whole atom. If the atom were a sports stadium, the nucleus would be a single grain of rice resting at the very centre of the field, with the electron somewhere out past the higher seats, and yet nearly all the weight is in that grain. The electrons are real, but they are feather-light. More than 99.9% of an atom's mass lives in the nucleus, so you have almost all the mass crushed into almost none of the volume, and that combination gives the nucleus a density that has no equal in everyday life. Picture it this way. If you could somehow strip out the empty space and pack nuclei directly against one another, a single cubic centimetre of that material, a piece the size of a sugar cube, would weigh something like 100 million tons. That is the weight of a small mountain, held in your fingertips. You never feel that density, because you never reach it. The empty space inside atoms always holds you off. But nature does reach it, out in the dark when a large star dies. When a massive star runs out of fuel and its core collapses, gravity crushes the matter so hard that the atoms cave in. Electrons are forced into the nucleus, the empty space is squeezed away, and what remains is essentially one vast nucleus the size of a city. We call it a neutron star. A spoonful of it would outweigh every car, ship, and building on a continent. The same density that hides in the speck at the centre of every atom is sitting there, laid bare, spinning in space. So the nucleus is the source of an atom's heft, its hard, heavy, almost unimaginably concentrated core. When Rutherford's alpha particles bounced back from the gold foil, this is what they struck, this tiny, dense knot of positive charge. They could not pass through it. They hit something with real mass packed into a point and were thrown back the way they came, It helps to hold the full picture in your mind now, the whole atom at once. At the centre, a fierce little nucleus, positive, heavy, 100,000 times smaller than the atom. Around it, the electrons, light and negative, filling out the atom's size with their motion. Between them, almost entirely empty space. The chemistry you learned, the way elements bond and react and burn, all of that happens out in the electron cloud, in the soft outer regions where atoms meet. The nucleus mostly sits at the centre, unbothered, holding the mass and setting the charge. But that fierce little centre raised a question the moment it was understood. Rutherford had shown the nucleus carried positive charge, and a lot of it. In a heavier atom, that meant many positive charges crowded into one tiny speck. And here is the trouble. Like charges push each other apart, hard, and the closer you force them, the harder they push. Two positive charges crammed into the cramped space of a nucleus should repel each other ferociously and blow the whole thing apart in an instant. Yet nuclei do not fly apart. They sit there, stable, for billions of years, holding their positive charges packed together against a repulsion that should be overwhelming. Something inside the nucleus was holding it shut, some force stronger than the electric push, working only across that tiny distance. Before anyone could name that force, they first had to learn exactly what was crammed inside the nucleus, and one of those pieces had been hiding, carrying no charge at all. By the 1920s, physicists knew the nucleus carried positive charge, and they knew where that charge came from. The nucleus contained protons, particles each carrying 1 unit of positive charge, the mirror of the electron's negative one but nearly 2,000 times heavier. Rutherford himself had identified the proton and given it its name, from a Greek word meaning first. The number of protons in the nucleus decided which element you had. 1 proton made hydrogen, 2 made helium. 6 made carbon, 8 made oxygen, 79 made gold. The proton count was the identity of the atom, the entry number on the periodic table, but the protons alone did not add up. When physicists weighed atoms, the nucleus was consistently about twice as heavy as its protons could explain. A helium nucleus had 2 protons, yet it weighed about as much as 4. Carbon had 6 protons and weighed about 12. Something else was in there, something with mass but no charge, since the charge already matched the protons exactly. For years, this was an awkward gap. People proposed that extra protons hid inside paired with extra electrons to cancel their charge, a clumsy fix that never sat right. The answer came in 1932 from James Chadwick, working at the Cavendish Laboratory in Cambridge under Rutherford. Other researchers had noticed a strange, very penetrating radiation coming off certain elements when they were struck by alpha particles. This radiation carried no charge, so it slipped through matter easily, unbothered by the electric fields that would deflect a charged particle. Some thought it was a form of high-energy light. Chadwick suspected it was a particle, a neutral one, and he designed careful experiments to weigh it by watching it knock protons out of other materials. From how hard it could kick a proton, Chadwick worked out the mass of the mystery radiation, and it came out almost exactly equal to the protons. Here was the missing piece, a particle with nearly the proton's mass but no charge at all. He called it the neutron for its neutrality. In a single set of experiments, the long-standing weight gap closed. A helium nucleus had 2 protons and 2 neutrons, 4 heavy particles, which matched its weight of 4. Carbon had 6 protons and 6 neutrons. The neutron was the silent partner that made up the missing mass. The neutron also explained something chemists had puzzled over for decades. Some atoms of the same element weighed slightly different amounts, even though they behaved identically in every chemical reaction. These are called isotopes. Now it made sense. The proton count fixed the element and never changed, but the neutron count could vary. Carbon almost always has 6 protons, but it might carry 6, 7 or 8 neutrons. Same element, same chemistry, slightly different weight. The neutrons added mass without touching the atom's identity. With Chadwick's discovery, the nucleus finally had a clear roster. It was built from two kinds of particle, protons and neutrons, packed tightly together. Together they are called nucleons, the builders of the nucleus. The protons set the charge and named the element. The neutrons added mass and made the heavier nuclei possible. A gold nucleus, the one that bounced Rutherford's alpha particles, held 79 protons and over 100 neutrons crammed into that impossibly small space. The neutron quickly became one of the most useful tools in all of physics. Because it carries no charge, it can drift right up to a nucleus without being pushed away and slip inside. That ability would later split the atom and unlock nuclear energy, for better and for worse. But in 1932, its first gift was simply clarity. The nucleus was protons and neutrons, and the count of each told you everything about which atom you held, which brought the old puzzle back, now sharper than before. The protons were still there, still positive, still crammed together, still pushing each other apart with tremendous force. The neutrons added no charge to calm them, so the question only grew more urgent: what was holding all those protons together? Put two magnets together the wrong way and you feel it in your hands, that firm, springy refusal as like poles shove each other apart. Electric charge does the same thing. Two positive charges repel, two negative charges repel, and the force grows fierce as you push them closer. This repulsion is not gentle. It is one of the strongest everyday forces there is, and it falls off slowly with distance, reaching across whole rooms when the charges are large enough. It is the same force that crackles in static and snaps in a spark. Now remember what sits inside the nucleus. In a heavy atom, dozens of protons are crammed into a space 100,000 times smaller than the atom itself. Every one of them is positive. Every one of them pushes hard on every other. And because they are forced so unbelievably close together, that push is not mild but immense. By the ordinary rules of electric charge, the nucleus should not exist for even a flicker of time. It should detonate the instant it forms, flinging its protons apart in every direction. Yet, it holds. Most nuclei sit perfectly stable year after year for the entire age of the universe. The carbon in your body has held its protons together for billions of years, since long before the Earth formed, inside some ancient star and ever since. Something in there is winning a tug of war against one of the strongest forces we know, and winning it easily, across the tiny span of the nucleus. Whatever that something is, it has to be stronger than electric repulsion, at least up close. This is the glue problem, and naming it clearly is the key to the next stretch of the descent. There must be a force, previously unknown, that pulls protons and neutrons toward one another. It has to be powerful enough to overwhelm the fierce electric push between protons, and it has to act only over a tiny range, because we never feel it outside the nucleus. Two protons an inch apart feel only repulsion. The same two protons touching inside a nucleus feel a powerful attraction that overrides that repulsion completely. The force switches on only at the shortest distances. Physicists named it almost plainly. They called it the strong force, or the strong nuclear force, because it was simply the strongest of all. It is the force that holds every nucleus together, the force that lets matter be heavier than hydrogen. Without it, there would be no carbon, no oxygen, no iron, no gold, nothing but lone protons drifting apart, unable to combine. The strong force is the reason there is a periodic table at all, the reason the universe could build anything more complicated than the simplest atom. But naming a force is not the same as understanding it, and the strong force kept its secrets for a long time. At first, it looked like a force between protons and neutrons, a kind of glue passed back and forth between them. In 1935, the Japanese physicist Hideki Yukawa proposed that nucleons hold together by trading a particle back and forth, and from the short range of the force he even estimated the mass of that particle. He was on the right track, and the particle he predicted was eventually found. But the deeper truth was stranger than a simple glue between protons. The strong force was a hint that protons and neutrons were not the bottom floor. The full story of why the nucleus holds together would only make sense once physicists realized that protons and neutrons are not simple, solid balls at all. They have an inside. The strong force is not really glue between nucleons. It is the faint outer reach of a far more powerful force working inside each one. But before anyone could see that far down, the world of particles was about to become much more crowded and much more confusing than anyone expected. For a while, the picture looked almost finished. Everything was built from 3 pieces. Protons and neutrons made the nucleus, electrons surrounded it, and that was matter. 3 particles, clean and complete. Add the photon, the particle of light, and you nearly had the whole inventory of the world. Physicists in the 1930s could be forgiven for thinking the hardest work was behind them, and only details remained. Then the sky started handing them new particles. High in the atmosphere, fast particles from deep space, called cosmic rays, crash into the air and shatter into sprays of other particles. When physicists carried their detectors up mountains and flew them in balloons, they began finding things that did not fit. In 1936, Carl Anderson and Seth Neddermeyer found a particle that behaved like a heavy electron, about 200 times heavier, with the same charge. Nobody had ordered it. It was named the muon. The physicist Isidore Rabi reportedly greeted it with a famous complaint, asking who had ordered that. Nothing in the tidy 3-piece picture called for a fat copy of the electron. After the war, the trickle became a flood. New machines called particle accelerators could push protons to enormous speeds and smash them into targets, and in those collisions, briefly, dozens of new particles appeared. There were pions, the particles Yukawa had predicted for the strong force. There were kaons, which behaved so oddly that physicists called their property strangeness, a name that stuck and became a real technical term. There were heavy cousins of the proton with names like lambda, sigma, and xi. Each carried its own mass, charge, and lifetime, and most of them lived for only the tiniest sliver of a second before decaying into something lighter. By the 1950s and early 60s, the count had climbed past 100. Physicists started calling it the particle zoo, half in wonder and half in despair. The whole point of fundamental particles was that they were supposed to be few. A handful of simple pieces, combined in different ways, was meant to explain the endless variety of the world. Instead, the supposed bottom floor was as crowded and varied as the world above it. The great physicist Enrico Fermi, asked to name all these particles, is said to have remarked that if he could remember the names of all of them, he would have become a botanist. The crowding was not just untidy, it was a sign that something was wrong, or at least missing. When the simplest level of nature turns out to have 100 different members, that is usually a clue that you're not looking at the simplest level at all. The chemists of the 1800s had faced the same kind of warning. They had 90-odd elements, far too many to be truly fundamental, and the sheer number eventually pointed toward a smaller set of pieces underneath, the protons, neutrons, and electrons. 100 particles in the zoo carried the same message. There was probably a deeper, simpler layer below, and these 100 were combinations of it. The particles did not arrive in pure chaos. As physicists sorted them by their masses, charges, and that strange new property called strangeness, patterns began to show. Certain particles fell naturally into neat groups, families of 8 or 10, arranged in tidy geometric shapes when you plotted their properties. The patterns were too clean to be accidents. They looked like the patterns chemists had once seen in the periodic table, the kind of regularity that hints at hidden structure underneath, at a smaller set of building blocks arranged in different combinations. Reading those patterns took a particular kind of mind, willing to trust the geometry even before anyone could see the pieces making it. 2 physicists working separately did exactly that. They proposed that the whole crowded zoo was built from just a few new particles, combined in simple ways, and one of them gave those particles a strange and lasting name. In 1964, 2 physicists independently looked at the crowded zoo and saw a way to clean it up. One was Murray Gell-Mann at the California Institute of Technology. a famously brilliant and sharp-tongued man with a love of languages and odd names. The other was George Zweig, who had been Gell-Mann's student and was working at the same time at a laboratory in Geneva. They arrived at nearly the same idea by different routes. Almost every particle in the zoo could be explained if it were built from a small number of deeper, more basic pieces. Gell-Mann called these pieces quarks. He took the word from a line in a difficult novel by James Joyce, 3 quarks for muster mark, partly because his idea needed the quarks to come in threes. Zweig, reaching the same conclusion, called them aces. Gell-Mann's name won, and quark is what we say today. The idea was that the heavy particles of the zoo, the protons, neutrons, and all their strange cousins, were not fundamental at all. Each was a small cluster of quarks bound together. At first, only 3 kinds of quark were needed, and they were given plain, almost playful names. There was the up quark, the down quark, and the strange quark. By combining these 3 in 2s and 3s, you could account for the whole sprawling family of heavy particles. A proton was 2 up quarks and 1 down quark. A neutron was 2 down quarks and 1 up. The strange particles, the ones with that odd property, simply contained 1 or more strange quarks. The 100 members of the zoo collapsed into a few recipes built from a tiny set of ingredients. The quark idea carried one feature so strange that it made many physicists doubt the whole thing. Quarks had to carry fractional electric charge. Every particle anyone had ever measured carried a charge that was a whole number times the electron's charge, 1 unit, 2 units, or none. Quarks broke that rule. The up quark carried 2/3 of a unit of positive charge. The down quark carried 1/3 of a unit, negative. No one had ever seen a fraction of the basic charge. To many, that made quarks look like a bookkeeping trick, a clever way to organise the patterns rather than real objects you could ever find. Gell-Mann himself was cautious at first about whether quarks were physically real or just a useful mathematical scheme, and the fractional charges fit together with eerie precision. Take a proton, 2 up quarks, and 1 down. 2/3 plus 2/3 is 4/3, minus 1/3 for the down quark, leaves exactly 1 whole unit of positive charge, precisely the proton's charge. A neutron, 2 downs and 1 up, gives 1/3 minus 1/3 minus 1/3 plus 2/3, which comes to exactly 0, precisely the neutron's neutrality. The fractions, strange as they were, added up perfectly to the whole number charges everyone already knew. The same scheme that organised the zoo also made a bold prediction. The patterns of particles, those neat families of 8 and 10, had a gap. 1 slot in a family of 10 was empty, and the quark scheme said a particle must sit there, with a specific charge, a specific strangeness, and a specific mass. Gell-Mann pointed to the gap and named the missing particle the omega minus. In 1964, in a detector at Brookhaven National Laboratory, it appeared, with very nearly the properties he had predicted. A theory that can call a new particle into view before anyone has seen it is doing something right. Still, a prediction confirmed is not the same as seeing the thing itself. Quarks remained, for the moment, ink on paper, 3 fractional pieces that made the arithmetic work beautifully. To believe in them fully, physicists wanted to reach inside a proton and feel the quarks directly. That meant building a machine that could see at a scale no one had ever probed, and firing into the proton the same way Rutherford had once fired into the atom. The way to see something very small is to hit it with something even smaller, and watch how it bounces, and physicists already had the example to follow. Rutherford had found the nucleus by firing alpha particles at gold, and studying the ones that bounce back hard. To look inside the proton, physicists would do the same thing 1 level down. They would fire electrons at protons, very fast electrons, and watch how they scattered. If the proton were a soft, smooth blob of charge, the electrons would deflect only gently. If it had hard pieces inside, some electrons would bounce off at sharp angles, just as the alpha particles had off the nucleus. To push electrons hard enough, they built a remarkable machine. At Stanford University in California stands a straight accelerator 2 miles long, the Stanford Linear Accelerator Center, known as SLAC. It drives electrons down its length until they are moving a hair under the speed of light, carrying enormous energy. A fast electron has a small reach. The faster it goes, the finer the detail it can resolve, so these near-light speed electrons could probe distances far smaller than a proton. In the late 1960s, a team there began firing them into a target of liquid hydrogen, essentially a tank of bare protons, and watching where the electrons went. The experiments were led by Jerome Friedman, Henry Kendall, and Richard Taylor, and they ran for years, patiently collecting how often electrons scattered and at what angles. The crucial measurements were the hard scatters, the electrons that came off at large angles having lost a lot of energy. These are called deep inelastic scattering. Deep because the electron probes deep inside, inelastic because the proton is shaken apart in the process rather than bouncing cleanly. The rate of those hard scatters held the answer to whether the proton had structure. The results carried the same shock Rutherford had felt. Far more electrons bounced off at sharp angles than a soft, smooth proton could explain. The electrons were striking small, hard, point-like objects inside the proton and ricocheting off them. The proton was not a uniform ball of charge. It had pieces inside, tiny concentrated centers that turned the electrons sharply, exactly as a few hard grains would. It fell to the theorists to connect those hard grains to quarks. Richard Feynman, working out what the scattering should look like, described the proton as containing small point-like constituents, which he cautiously called partons, meaning parts. James Bjorken found a precise pattern the data should follow if those parts were truly point-like, and the data followed it. As the analysis deepened, the partons matched the quarks exactly. They had the right fractional charges, the right number, the right behavior. The point-like grains inside the proton were Gell-Mann's quarks, no longer ink on paper but real objects scattering real electrons. This was the turning point that made quarks physical. Before the Stanford experiments, quarks were a beautiful scheme that organized the zoo and predicted the omega minus, but no one had touched one. After Stanford, there was direct evidence. Fire an electron into a proton, and it bounces off something small and hard inside, and that something behaves precisely as a quark should. Friedman, Kendall, and Taylor later shared the Nobel Prize for showing the proton has parts. So the proton joined the atom and the nucleus as another thing once thought simple that turned out to have an inside. The atom held a nucleus and electrons. The nucleus held protons and neutrons. And now the proton held quarks, 3 of them, small and hard and carrying their strange fractional charges. But the experiment showed something else, something puzzling. Inside the proton, the quarks moved almost freely as if barely held. Yet no one could ever knock one out and catch it alone. That contradiction pointed to a force unlike any other. The strange thing about the quarks inside the proton was how they moved. When the fast electrons at Stanford struck them, the quarks behaved as if they were nearly free, rattling around inside the proton almost as though nothing held them at all. A struck quark recoiled cleanly, the way a loose marble would, and yet, no matter how hard the experiments hit the proton, no single quark ever came flying out to be caught on its own. The quarks acted free inside their tiny prison, but the prison had no door. This is a strange pairing of facts, and it told physicists they were dealing with a force unlike the others they knew. Both gravity and the electric force behave the same way. They are strongest when objects are close, and weaken as the objects move apart. The force-binding quarks does the opposite. When quarks sit close together, the force between them is feeble, almost nothing, which is why they rattle around freely inside the proton. When you try to pull 2 quarks apart, the force grows stronger. It behaves less like glue, and more like an unbreakable elastic band that pulls harder the more you stretch it. The particle that carries this force is the gluon, named for the obvious reason that it glues quarks together. Just as the electric force between charged particles is carried by photons, particles of light passed back and forth, the strong force between quarks is carried by gluons passed between them. But gluons are far stranger than photons. A photon carries the electric force without itself being electrically charged. A gluon carries the strong force while itself being subject to the strong force, so gluons pull on each other as well as on quarks. That self-pulling is part of why the force behaves so unusually, tightening rather than fading as quarks separate. This is the true strong force, and it lives inside the proton and neutron. The theory describing it is called quantum chromodynamics, a long name for the rules governing quarks and gluons. The faint glue that holds the nucleus together, the strong nuclear force that overwhelms the electric repulsion of the protons, turns out to be only a leftover whisper of this deeper force. The real strong force binds quarks inside each proton and neutron. What reaches out between neighbouring nucleons to hold the nucleus shut is just the small part of it that spills past the edges, like warmth leaking from a sealed furnace. Now you can finally answer the glue problem from earlier. The protons in a nucleus do repel one another fiercely with their like charges, but each proton and neutron is itself a knot of quarks bound by the overwhelmingly stronger gluon force, and a little of that force reaches between neighbours and binds them too. The strong force, even in its leaked-out, weakened form between nucleons, is more than enough to overpower the electric repulsion. That is why the nucleus holds, why carbon and iron and gold exist, traced all the way down to gluons gripping quarks. The elastic band behaviour also explains why a lone quark is never found. As you pull a quark away from its partners, the force between them does not fade. It stays strong, and the energy stored in that stretching grows and grows, like stretching a band until it could snap. But in this case, when enough energy builds up, the band does not simply break and release a free quark. Something stranger happens, dictated by the rules of this force, and by a property of quarks no one has mentioned yet, a property that comes in 3 varieties, and that gives the whole theory its colourful name. Quarks carry a kind of charge that has nothing to do with electricity, and physicists, half in fun, gave it the name colour. It has nothing to do with real colour, with light, or with what your eyes see. It is simply a label for a new kind of charge that quarks possess, and that the strong force responds to, the way the electric force responds to electric charge. They chose colour because this charge comes in 3 varieties, and 3 is also the number of primary colours that combine to make white light. So the 3 colour charges were named red, green, and blue. The rule that governs colour is simple to state and strict. Nature only allows particles whose colours combine to cancel out, to come to what physicists call colourless or white. There are 2 ways to do that. You can put 3 quarks together, 1 red, 1 green, 1 blue, and the 3 colours balance to white, just as red, green, and blue light combine to white. That is exactly what a proton or a neutron is, 3 quarks in 3 different colours, balanced. Or you can pair a quark of one colour with an antiquark carrying the matching anticolour, and they cancel. That pairing makes the lighter zoo particles, the pions and kaons, a quark and an antiquark together. This colour rule is why you never find a lone quark, and the reason has a name: confinement. A single quark by itself would carry one colour and would not be colourless, and nature forbids that. So quarks are confined, locked permanently inside colourless bundles, never allowed to wander out alone. The proton holds its 3 quarks the way a sealed jar holds what is inside, except the seal can never be opened. Every quark you will ever find is bound up with others into a colourless whole. Now, return to the stretching band from the last chapter, the quark you tried to pull free. As you pull it away from its partners, the strong force does not weaken, and the energy stored between them keeps climbing. At some point, that stored energy becomes so large that it is enough, by Einstein's relation between energy and mass, to create new particles outright. The energy converts into a fresh quark and antiquark pair, springing into being in the gap. Instead of one lone quark coming free, The gap fills with new quarks that immediately pair up into new colourless particles. You pulled to get one quark alone and got two bundles instead. The quark is never isolated, only multiplied. This is one of the deepest features of nature and one of the least known outside physics. The pieces inside the proton can never be taken out and set on a table to look at, not because our tools are too weak, but because the laws themselves forbid a quark to exist alone. We know quarks are there. We have scattered electrons off them and measured their charges and counted them, yet we can never hold one. They are real and permanently hidden at the same time, sealed inside the particles they build. The strange behaviour the Stanford experiment saw now fits together. Up close, inside the proton, the strong force is weak, so the quarks rattle nearly free, and this property is called asymptotic freedom. The physicists who worked out the theory behind it, David Gross, Frank Wilczek, and David Politzer, later shared the Nobel Prize for it. Pull the quarks apart and the force strengthens until new particles are born rather than a free quark released. Weak when close, strong when stretched, colourless always. Those rules govern everything the strong force does, and those rules carry a consequence that reaches into your own body, into the very weight of you. The proton is mostly empty of solid matter, its three quarks almost weightless. Yet the proton has real, substantial mass. That mass has to come from somewhere, and the answer turns the everyday idea of weight upside down. Here is a fact that sounds impossible the first time you hear it. The three quarks inside a proton account for only a tiny fraction of the proton's mass, around 1% of it. Add up the weight of the two up quarks and the one down quark, and you get almost nothing compared to the proton as a whole. Yet the proton has a definite solid mass, the mass that makes up nearly all of your body. If the quarks barely weigh anything, then almost all of that mass, 99% of it, comes from something other than the quarks themselves. That something is energy. Inside the proton, the quarks are not sitting still. They move at tremendous speeds, and the gluons fly between them carrying the strong force, and the whole interior churns with the energy of that ceaseless, furious binding. Einstein's famous relation, that energy and mass are two forms of the same thing, means that energy itself has weight. The energy of the quarks racing around and the gluons binding them is enormous, and that energy, by the rule that energy and mass are one, shows up as mass. Almost all the proton's weight is the weight of the motion and the binding inside it. Sit with what that means for the table and for your hand resting on it. You learned long ago that solid things are made of matter, of stuff with substance, but the substance turns out to be mostly not stuff at all. Strip a proton down and you find three feather-like quarks and a storm of energy, and that storm is where the weight lives. The heft of the table, the weight of a stone, the number on your bathroom scale, almost all of it is binding energy. The energy of quarks and gluons locked in their furious dance. You are, by weight, almost entirely motion and force, with only the faintest trace of actual particle mass. This flips the everyday picture of mass on its head. We tend to think mass is the amount of solid material in a thing, the count of how much stuff it contains. But for ordinary matter, that is not where the mass mostly comes from. The mass comes from energy bound up inside, energy held in place by the strong force. The quarks supply the seeds, the points that the force acts on, but the weight is in the binding. Matter is mostly the energy of its own holding together. There is one piece this does not cover, and it is worth being honest about. The quarks do have some small mass of their own, that 1%, and so does the electron, and those small masses come from somewhere else entirely, from a different mechanism we have not reached yet. So not all mass is binding energy, but for the ordinary matter you're made of, for protons and neutrons, and therefore for nearly your whole body weight, the overwhelming majority of the mass is the energy of the strong force at work inside. The small leftover, the intrinsic mass of the quarks, waits for a later chapter and a different field. So the solid world thins out further the closer we look. The atom was mostly empty space. The nucleus was a speck. The proton inside it is 3 tiny quarks in a storm of energy, and that storm is most of the weight. At every level, the solid, substantial thing you started with dissolves into something sparser and stranger, held together by force and motion rather than by packed material, and there is one more dissolving to come, the deepest yet. So far we have pictured all these pieces, electrons and quarks and the rest, as tiny objects, little balls or points, however small. That picture, the last comfortable picture of particles as things, is about to be set aside as well. The truest description does not start with particles at all. It starts with fields. We have been picturing the pieces of matter as tiny objects, little specks or grains, the electron as a minute ball, the quark as a hard point. That picture has carried us a long way down, and it is time to set it gently aside, because it is not how the deepest layer of physics actually works. At the bottom, the world is not made of little balls at all. It is made of fields, and the particles are ripples in them. Start with a field you already know. A magnet has a magnetic field around it, an invisible influence filling the space nearby, strongest close to the magnet and fading with distance. You have felt it through the tug on a second magnet or seen it in the way iron filings line up around the poles. A field is just a quantity that has a value at every point in space, something spread out everywhere rather than located in one spot. The magnetic field is real, it carries energy, and it fills the room even though you cannot see it. The deep idea of modern physics, the framework called quantum field theory, is that everything is made of fields like this, spread through all of space. There is a field for the electron, filling the entire universe, present at every point. There is a field for each kind of quark, and a field for the photon, which is the electromagnetic field, and a field for every other fundamental particle. These fields are the real, basic things. They are not in space the way objects are. They are spread across all of it, the deepest fabric there is. A particle, in this picture, is a ripple in its field, a small packet of vibration that travels along. An electron is a tight ripple in the electron field. A photon is a ripple in the electromagnetic field. When you see a flash of light, you're seeing ripples in that field reaching your eye. The reason every electron in the universe is exactly identical, the same mass, the same charge, never the slightest variation, is that they are all ripples in the same single field, like identical waves on one ocean. There is no factory stamping out electrons to match. There is one electron field, and every electron is a vibration in it, so of course they are all the same. This explains something that the little ball picture never could. Particles can appear and disappear. In high-energy collisions, particles are created out of energy and others vanish, turning into different ones entirely. If particles were tiny permanent objects, this would make no sense. Objects do not simply blink into being or wink out. But ripples can. A field can be still, then take on a ripple where there was none, and that is a particle appearing. The ripple can fade or pass its energy to another field, and that is a particle vanishing. The world of fields allows exactly the creation and destruction we see. So the final, truest picture is stranger and emptier than any before it. There is no tiny solid grain at the bottom of things. There are fields spread everywhere, and particles are the ways those fields can ripple and vibrate. Your hand on the table is one set of ripples meeting another, the electron fields in your skin pushing on the electron fields in the wood, all of it patterns in fields that fill the universe. The little balls were a useful story. The fields are what is really there, and this picture has a consequence that overturns the last comfortable idea we have left, the idea of empty space. If fields fill all of space, then even space with no particles in it, the truest emptiness you can imagine, still has the fields running through it. A field can never be perfectly, absolutely still, and that means empty space is not empty at all. Think about the emptiest place you can imagine. Not a room with the air pumped out, but truly empty space, far between the stars, with every particle removed, every speck of matter, every trace of light. That is the vacuum, nothing at all, the very picture of emptiness. For most of the history of physics, that is exactly what the vacuum was thought to be. A stage with nothing on it, a perfect and quiet nothing waiting to be filled. The picture of everything as fields changes this completely. The fields are everywhere, filling all of space, and they remain even when you remove every particle. Emptying a region of all its particles does not remove the fields. It only means the fields have no ripples in them at that moment, no particles riding along. The electron field is still there, the electromagnetic field is still there, every field still threads through the empty region. The vacuum is not the absence of fields, it is the fields at their lowest, quietest state. And here the quantum part enters and changes everything. A quantum field can never be perfectly, completely still. The rules of quantum physics forbid it through what is called the uncertainty principle, which says certain pairs of quantities can never both be pinned to exactly zero at once. A field sitting at perfect dead stillness would be too precisely fixed to satisfy that rule. So even in the emptiest vacuum, the fields cannot lie flat and motionless. They quiver. They carry a faint, restless, unavoidable jitter, the smallest possible level of activity, which can never be removed no matter how much you cool or empty the space. This faint, irreducible activity is sometimes called the zero-point energy, the energy that remains when everything that can be taken away has been taken away. The vacuum, the truest emptiness there is, still hums with it. Every point in empty space carries this restless quiver in every field, a constant low seething that underlies what looks like perfect stillness. The nothing is not nothing. It is a quiet, ceaseless activity that fills all of space, even where no particle exists. Out of that quiver, something remarkable happens. The restless fields can, for the briefest instant, throw up a ripple, a particle that flickers into being and vanishes again almost immediately. These are not ordinary lasting particles. They appear borrowed from the vacuum's energy and are paid back so fast that they can never be caught directly. Pairs of them flicker in and out everywhere, all the time, a constant fizzing of fleeting particles appearing and disappearing throughout all of empty space. The vacuum is less like an empty stage and more like the surface of a pot just before it boils, never quite still. This is one of the strangest claims in all of physics, and it would be easy to dismiss it as a mathematician's fantasy, a quirk of the equations with no bearing on anything real. The fields jitter, fleeting particles flicker in and out, the vacuum seethes, all of it invisible and untouchable. A reasonable person might ask whether any of this can be tested, whether the seething vacuum makes any difference you could ever measure in the real world. It does, and that is what raises it from speculation to established physics. The restless vacuum leaves fingerprints, real effects that show up in careful experiments, measurable shifts and forces that would not exist if empty space were truly empty and still. Physicists have detected those fingerprints more than once with great precision. The flickering particles of the vacuum, borrowed and repaid in an instant, push on real objects and nudge real energy levels in ways we can see. Those measurements are how we know the empty space around you is quietly alive. The flickering particles of the vacuum are called virtual particles, and the word virtual matters. They are not quite real in the ordinary sense, not particles you can trap and study at leisure. They are borrowed, springing out of the vacuum's restless energy and paying it back so quickly that they vanish before they can be caught. The uncertainty principle allows this borrowing. It lets a tiny amount of energy appear, as long as it is returned fast enough, and the more energy borrowed, the faster it must be repaid. Across all of empty space, these borrowed particles flicker into being and wink out, constantly, everywhere. You cannot catch a virtual particle directly, but you can see what they do, and the first clear sign came from inside the atom. In 1947, Willis Lamb made an extraordinarily precise measurement of the energy levels of the hydrogen atom, the simplest atom there is, 1 electron around 1 proton. The best theory of the time predicted exactly where those energy levels should sit. Lamb found that two levels that were supposed to have precisely the same energy did not. One was nudged very slightly away from the other, by a tiny amount that should not have been there at all. This small gap became known as the Lamb shift. That tiny shift had an explanation, and the explanation was the seething vacuum. The electron in the hydrogen atom is not moving through empty nothingness. It moves through the restless vacuum, constantly surrounded by virtual particles flickering in and out around it. Those fleeting particles jostle the electron ever so slightly, nudging its path and shifting its energy by a minuscule amount. When physicists calculated how much the virtual particles should shift the energy levels, the number matched Lamb's measurement with stunning accuracy. The vacuum's restless activity had left a precise, measurable mark inside the simplest atom. There is a second fingerprint, even more striking because you can almost picture it. In 1948, Hendrik Casimir predicted that if you place two flat metal plates extremely close together in a vacuum, they will feel a faint force pulling them toward each other, with nothing between them to cause it. The reason lies in the virtual particles of the vacuum. The flickering activity of the electromagnetic field fills all of space, but between two closely spaced plates, only certain ripples fit. Fewer kinds of ripple can exist in the narrow gap than in the open space outside. So the vacuum pushes slightly harder from outside than from within, and the plates are pressed together. This is the Casimir effect, and the strangeness of it is worth holding on to. Two plates in a perfect vacuum, with nothing between them, no air, no field source, no particles, drift toward each other, pushed by the difference in the vacuum's own restless energy inside and out. It sounds like getting a force from nothing. The force is small, but it is real, and it has been measured directly in careful experiments. The empty space between the plates is doing something, pressing less than the empty space outside, and the plates respond. These two effects, the Lamb shift and the Casimir force, turn the seething vacuum from a strange idea into settled fact. The vacuum really is alive with virtual particles, and they leave marks we can measure with great precision. Empty space pushes on plates and nudges electrons. The emptiest nothing you can imagine is quietly busy, and that busyness has consequences in the real world. So the descent has carried us a long way from the solid table. Matter dissolved into mostly empty atoms, then into specks and quarks, then into ripples and fields, and now even the emptiness between things turns out to seethe with borrowed life. It is time to gather what we have found into a single picture, the full catalogue of the fundamental pieces, the most complete and successful description of matter that physics has ever built. We have been pulling matter apart piece by piece, and now we can lay the genuine pieces on the table, the ones with no smaller parts inside as far as anyone has ever found. The complete list of fundamental particles, together with the rules they follow, is called the Standard Model of Particle Physics. It is the hard-won result of a century of experiments and theory, and it is the most thoroughly tested description of the physical world ever assembled. Almost everything in this list was predicted on paper before it was found, and then found, often exactly where the theory said it would be. The matter you're made of comes from two small families. The first family is the quarks, and there are 6 of them. 3 you have already met, the up, the down, and the strange. The other 3 are heavier versions named charm, bottom, and top. Only the up and down quarks make up ordinary matter, joining in 3s to form the protons and neutrons of every nucleus. The 4 heavier quarks appear briefly in high-energy collisions and then decay, but they are real, and the top quark, the heaviest of all, was the last to be found, captured at the Fermilab laboratory near Chicago in 1995. The second family of matter particles is the leptons, and there are 6 of these as well. The electron, you know, the familiar carrier of negative charge around every atom. It has 2 heavier cousins, the muon, that fat electron from the cosmic rays, and the tau, heavier still. Alongside these 3 sit 3 ghostly partners called neutrinos, 1 paired with each. Neutrinos carry no electric charge and almost no mass, and they barely interact with anything at all. Trillions of them born in the Sun are streaming through your body as you read this, and nearly everyone passes through the entire Earth without touching a thing. So the matter particles number 12 in total, 6 quarks and 6 leptons, and they fall into a pattern of 3 repeating sets. But matter alone is not enough. The particles must push and pull on one another, and in the standard model the forces themselves are carried by particles. The electromagnetic force is carried by the photon, the particle of light, passed between charged things. The strong force is carried by the gluons gripping the quarks. The weak force, the one behind certain kinds of radioactive decay, is carried by 3 heavy particles called the W+, the W-, and the Z. These force-carrying particles are the messengers that let matter interact. There is one more piece, the most recently found and in some ways the strangest, and it stands apart from the rest. It is the Higgs particle, the ripple in a field that fills all of space and gives many of the other particles their mass. It was the last piece of the standard model to be predicted and the last to be found, and its discovery in 2012 completed the catalogue. We will come back to it properly because it answers the question left open earlier, where the small intrinsic mass of the quarks and the electron comes from. Lay it all out, and the whole of ordinary matter, every atom, every star, every living thing, is built from a startlingly short list. A handful of matter particles, mainly just the up quark, the down quark, and the electron for everything you see and touch. A few force carriers to bind them and let them interact, and the Higgs to give them mass. From this small set, combined and recombined, comes the entire material universe. The 100-member zoo collapsed into this clean, ordered table, and it works to extraordinary precision. It is one of the great achievements of the human mind, and it is also, on close inspection, full of holes. The standard model describes what the pieces are and how they behave, but it does not explain why they are what they are, why there are 3 families, why the masses take the values they do, or what gives the Higgs its power. The next stretch of the descent walks straight into those gaps, beginning with the field that answers where mass itself begins. We left one question open, where the small intrinsic mass of the quarks and the electron comes from. The strong force explains most of a proton's weight, the binding energy of its quarks and gluons. But the quarks themselves have a little mass of their own, and so does the electron, and that mass cannot come from binding. It comes from somewhere else, from a field that fills all of space and touches nearly every particle as it moves. That field is the Higgs field, and the story of finding it took almost 50 years. In 1964, several physicists working separately arrived at the same idea, among them Peter Higgs in Edinburgh and the pair François Anglais and Robert Brute in Brussels. They were trying to solve a technical problem in the theory of forces, but the solution they found had a sweeping consequence. They proposed that all of space is filled with an invisible field, present at every point, and that particles gain their mass by interacting with it. The more strongly a particle feels this field, the more mass it has. A particle that ignores the field entirely stays massless, and flies at the speed of light, as the photon does. The everyday picture people reach for is a field like a thick medium that particles must move through. Imagine walking across a room that's empty, and then walking across the same room filled shoulder to shoulder with a slow crowd. In the empty room you move freely. In the crowd you are slowed, pressed on, harder to push into motion and harder to stop. Mass is something like that resistance to being pushed, that reluctance to change speed. A particle that interacts strongly with the Higgs field is gripped by it, hard to accelerate, and we call that heaviness mass. The comparison is rough, and it breaks down if you lean on it too hard, but it carries the core of the idea. Here the comparison stops fitting, and the real physics shows through. The Higgs field does not slow particles by friction, the way a real crowd would drag you to a stop. It does not drain their motion. It gives them the property of having mass at all, the resistance to changes in motion that lets them be slow in the first place. Without the field, the electron would have no mass and could never sit quietly in an atom. With it, the electron gains its small, steady mass, and matter as we know it becomes possible. The field does not push back against motion. It sets the very cost of starting and stopping. A field like this should have its own ripple, its own particle, just as the electromagnetic field has the photon. That ripple is the Higgs particle, often called the Higgs boson. Finding it would be the proof that the field was real and not just a convenient idea. But the Higgs particle is heavy and hard to make, and it took a machine of enormous power to produce one even briefly. That machine was the Large Hadron Collider, a ring 17 miles around buried beneath the border of France and Switzerland, run by the laboratory called CERN. In the Large Hadron Collider, protons are driven to nearly the speed of light and smashed head-on, concentrating so much energy in one tiny spot that, now and then, a Higgs particle flickers into being and instantly decays. In 2012, 2 separate teams, each with thousands of physicists, announced that they had seen it. The signal stood clear in the data, a new particle with the mass the theory roughly expected. Peter Higgs, by then in his 80s, was in the room and wept. The field he had proposed half a century earlier was real, and the catalogue of the standard model was complete. Yet completing the catalogue did not explain it. The Higgs gives mass, but it does not say why each particle feels the field as strongly as it does, and that unanswered why grows louder when you notice matter comes in 3 near-identical copies. When physicists laid out the full list of matter particles, a strange regularity stared back at them. The pieces did not come as a single set. They came as 3 almost identical sets, stacked one on top of another, differing only in weight. Physicists call these the 3 generations of matter, and nothing in the standard model explains why there should be 3 rather than 1 or 7 or 1,000. Look at the first generation, the one that builds you and everything around you. It holds the up quark, the down quark, the electron, and the electron's ghostly neutrino. From the up and down quarks come protons and neutrons, and with the electron you have atoms, chemistry, and the whole material world. This first set is all that ordinary matter needs. Every atom in your body and the table in the stars overhead is built from just these few first-generation pieces. By themselves they would be enough to make a universe. But nature did not stop there. There is a second generation that copies the first exactly in every property but mass. In place of the up and down quarks sit the charm and strange quarks, heavier versions with the same charges. In place of the electron sits the muon, that fat electron from the cosmic rays, about 200 times heavier but otherwise the same. And there is a second neutrino to match. Every particle in this second set behaves like its first generation twin in all respects but one, its greater weight. They are like the same characters played by heavier actors. Then there is a third generation, heavier still. The top and bottom quarks stand in for up and down. The top quark so heavy it outweighs an entire atom of gold. The tau takes the place of the electron, heavier even than the muon, and a third neutrino completes the set. 3 full copies of the matter particles, identical in their charges and their roles, climbing in mass from the light first generation to the heavy third. The pattern is exact and the reason for it is unknown. The deep strangeness is that the extra 2 generations seem unnecessary. The universe of ordinary matter runs entirely on the first generation. The heavier copies are not woven into atoms or chemistry or life. They appear when enough energy is concentrated, in cosmic ray strikes and accelerator collisions, and then they decay within tiny fractions of a second back down into first-generation pieces. They flash into being and are gone. The world does not seem to need them, and yet there they are, 2 full spare sets, built into the deepest level of nature. This puzzle is old and still open. When the muon was found, and it became clear it was simply a heavier electron with no new job to do, Isidore Rabi asked his famous question, who ordered that? The question still has no answer. We can measure the 3 generations precisely. We can confirm from the behaviour of particles and from the early universe that there are exactly 3 and not a 4th. But we cannot say why 3, or why each is heavier than the last, or what sets the enormous gaps between their masses. The number 3 is simply read off from nature, not derived from anything deeper. It is worth pausing on how unusual this kind of ignorance is. The standard model predicts the outcomes of experiments to staggering precision, matching measurement after measurement to many decimal places. And yet at its heart sits this brute fact it cannot explain: 3 copies of matter rising in mass for no stated reason. The theory tells you what is there with great exactness, while staying silent on why. That silence is not unique to the generations. It runs through the very numbers that set the masses, numbers the theory cannot produce on its own. A working theory of physics is supposed to do more than name the pieces. At its best, it predicts numbers, the actual values that experiments will measure, derived from the theory's inner logic. The standard model does this brilliantly for many quantities, calculating them from first principles and matching experiment to astonishing precision. But for one whole class of numbers, the masses of the fundamental particles, it does nothing of the kind. Those numbers are not predicted. They are measured, written down by hand, and fed into the theory from outside. Consider what that means. The electron has a certain mass, a small and definite weight. The up quark has another, the down quark another, on up through the muon, the tau, the heavier quarks, the W and Z particles, and the Higgs itself. Each has its own particular mass, and the values are all over the map, spanning an enormous range from the nearly weightless neutrinos to the top quark, heavier than an atom of gold. The standard model needs every one of these values to work, but it cannot tell you a single one of them. Physicists measure them in experiments and then insert them into the equations as settings. The Higgs field, remember, gives each particle its mass according to how strongly that particle feels the field. So the question becomes why each particle feels the Higgs field exactly as strongly as it does. Why does the electron grip the field just hard enough to get its particular small mass, while the top quark grips it hundreds of thousands of times harder? The strengths of those grips are the unexplained numbers. Nothing in the theory sets them. They're dialed in to match what we observe, and the theory accepts whatever values we give it without offering a reason. These hand-entered numbers are called the free parameters of the standard model, and there are around 20 of them. 20 numbers that must be measured and inserted before the theory can run, 20 values that nature seems to have simply chosen. They include the particle masses, the strengths of the forces, and a handful of others. The theory is a magnificent machine, but it comes with 20 knobs whose settings it cannot derive, knobs whose positions we can only read off the universe and copy down. This bothers physicists deeply, and it should. A truly fundamental theory, the kind many hope to find, would have few free parameters or none. It would derive the electron's mass from something deeper, explain why it is exactly what it is and could not be otherwise. Instead, we have 20 arbitrary-looking values with no apparent pattern, no formula linking them, no reason offered for why the electron weighs what it weighs rather than twice or half as much. They sit at the base of our best theory like a row of dials set by an unseen hand. It is possible, of course, that there is no deeper reason, that the values are simply what they are, brute facts of our universe with no explanation behind them. Maybe the dials were set at random when the universe began and could have come out differently. But most physicists find that hard to accept. The numbers feel too important to be accidents. The electron's mass shapes the size of atoms. The strength of the forces shapes whether stars can burn and whether chemistry can happen. Small changes in these dials would give a dead universe. That they sit where they do, allowing a world rich enough to hold us, makes the lack of explanation sting all the more. One of these numbers stands out above the rest, a pure number with no units attached, that has haunted physicists for nearly a century. It governs the strength of the electromagnetic force, and its value, close to 1/137, has never been explained by anyone. Most of the numbers in physics carry units. A speed is so many miles per hour, a mass so many grams, and the number you write down depends on the units you chose. Change from miles to kilometers, and the number changes, though the speed is the same. But a few numbers in nature are pure, just numbers, the same to any observer using any units anywhere. These are the ones physicists watch most closely, because they cannot be explained away as artifacts of our measuring system. They are properties of the universe itself. The most famous of them is called the fine structure constant. The fine structure constant sets the strength of the electromagnetic force, how strongly charged particles push and pull on one another and on light. Its value is very close to 1/137. That is the whole number, a plane ratio with no units, the same for a physicist on Earth and one in a distant galaxy. It first appeared in the early 20th century, when Arnold Sommerfeld was refining the theory of the hydrogen atom, and found this number governing the fine details of its light, the small splittings in its spectral lines. That is where the name fine structure comes from. What makes this number haunting is that nothing explains it. It is not predicted by any theory. It is measured, and it comes out near 1/137, and no one knows why that value and not another. If it were much larger, the electromagnetic force would be stronger, and atoms and chemistry would work differently or not at all. If it were much smaller, the same. The world we have depends on this number sitting close to where it does, yet it appears to be set arbitrarily, one more dial on the face of nature with no reason given for its position. The number drew something close to obsession from the physicists who lived with it. Wolfgang Pauli, one of the sharpest minds of the quantum age, was fascinated by it his whole life, by the strange particular value of 1/137. There is a story, perhaps too neat to be entirely true but often told, that Pauli died in a hospital room numbered 137. The number had followed him through his work, and there it was at the end. Whether the tale is exact or not, it captures how deeply this plane ratio worked its way into the minds of the people who studied it. For a long time, people hoped the number might come out of some simple formula, that 1/137 could be built from other known constants in a clean way. Many tried, none succeeded. The value is not exactly 1/137, but slightly off, a precise measured figure with many decimal places, and no neat formula has ever produced it. Worse, physicists later learned the number is not even truly constant. Its effective value changes slightly depending on the energy at which you probe, creeping upward when charged particles meet at very high energies. So even the fixed number is not quite fixed. The fine structure constant stands as the clearest single example of the larger problem. Here is a pure number, central to how the universe works, woven into every atom and every ray of light, and our best physics cannot say why it has the value it has. It is measured and inserted like the masses, an arbitrary dial whose setting we read off the world. The deepest theories we have describe what the electromagnetic force does with extraordinary accuracy, while staying completely silent on why it has exactly this strength. These arbitrary numbers are humbling, but the same equations that leave them unexplained have also, at their best, reached ahead of experiment and called whole new worlds of matter into view. One equation in particular did something that still seems almost magical, predicting a hidden mirror of all matter from pure mathematics alone. In 1928, a young English physicist named Paul Dirac sat down to fix a mismatch between two great theories. Quantum mechanics described the small world of particles. Einstein's relativity described fast motion and the link between energy, mass, and the speed of light. The equation physicists had for the electron worked in the quantum world but did not respect relativity. Dirac wanted one equation that honoured both, that described an electron moving quickly and quantum mechanically at once. He was a quiet, intensely precise man who trusted mathematics over intuition, and he chased the equation through its own internal logic. He found it, and it was beautiful. The Dirac equation described the electron perfectly, accounting for features that had been put in by hand before, including the electron's spin, a kind of built-in rotation. It was one of those rare equations that seems to know more than its author did, capturing the electron's behaviour with a depth that felt discovered rather than invented. But the equation had a peculiar feature that Dirac could not ignore. Along with the ordinary electron, it described another solution, a particle just like the electron but with the opposite electric charge, positive instead of negative. At first, this extra solution looked like a flaw, a piece of mathematical debris that ought to be explained away. There was no such thing as a positive electron. Dirac wrestled with what the second solution could mean, trying various interpretations, none quite satisfying. In the end, he took the bold step of trusting the equation over the absence of evidence. He proposed that the extra solution was real, that there existed a genuine particle with the electron's mass but the opposite charge, a mirror image partner to the electron. The mathematics demanded it, so he predicted it. In 1932, Carl Anderson, studying cosmic rays with the same kind of detector that would later reveal the muon, found Dirac's particle. In the tracks left by cosmic ray collisions, he saw a particle that curved the wrong way in a magnetic field, exactly as a positive electron would. It had the electron's mass and the opposite charge, just as the equation had said 4 years earlier. It was named the positron, the antiparticle of the electron, and it was the first piece of antimatter ever found. Dirac had predicted a new form of matter from pure mathematics, and the universe produced it. This opened up a hidden symmetry running through all of matter. The positron was not a special case. Every kind of particle, it turned out, has an antiparticle, a mirror twin with the same mass and opposite charge. The proton has the antiproton, the antiquarks pair with the quarks, and so on through the whole catalogue. For every piece of matter there is a piece of antimatter, an opposite written into the structure of nature. When a particle meets its antiparticle, the two annihilate, vanishing in a flash of pure energy, their entire mass converted to light by Einstein's relation between mass and energy. Antimatter is real, and we make it and handle it today. Hospitals use it routinely in the scan called positron emission tomography, a PET scan, which works by detecting the tiny flashes of light made when positrons from a special dye meet electrons in the body. The antimatter Dirac dreamed out of an equation now helps doctors see inside living people. What began as an awkward second solution, almost discarded, became a tool resting in ordinary hospitals. The deeper lesson is about the power hiding inside the right equation. Dirac was not looking for antimatter. He was trying to make two theories agree, and the mathematics, followed honestly, handed him a whole mirror world of matter no one had imagined. This happens again and again in physics, that a demand for consistency, for the equations to respect some symmetry, forces new truths into the open. Symmetry, it turns out, is not a side feature of the laws. It may be the deepest source of the laws themselves. There is a quiet idea underneath all of modern physics, so simple it is easy to miss, and so deep it may be the root of everything else. The idea is symmetry. In everyday speech, symmetry means a kind of balance, the way a face or a snowflake looks the same on the left as on the right. In physics, it means something close to that but more precise, that you can change something about a situation, and the laws of physics stay exactly the same. A symmetry is a change that makes no difference to the rules. Take a simple example. Do an experiment here, then carry the whole setup a mile to the east and do it again. You get the same result. The laws of physics do not care where you are. They work the same in every place. That sameness across locations is a symmetry. Or do the experiment today, then do it again next week. The laws are the same in time too, unchanged from one moment to the next. Or turn your whole apparatus to face a different direction. Again, the same laws apply. These sound almost too obvious to mention, mere common sense about a lawful world. In 1915, a German mathematician named Emmy Noether proved that these obvious-seeming symmetries are not idle at all. She showed, in a theorem of startling power and beauty, that every continuous symmetry in the laws of physics is tied to a conserved quantity, something that cannot be created or destroyed. Where there is a symmetry, there is a thing nature keeps perfectly constant, and the two are locked together. This single result, now called Noether's theorem, became one of the central pillars of all physics. Symmetry and conservation are two faces of one truth. The connections she revealed are exact and astonishing. The symmetry of the laws across different places, the fact that physics is the same here and a mile east, is tied directly to the conservation of momentum, the quantity of motion that never changes in a closed system. The symmetry across time, the sameness of the laws from one moment to the next, is tied to the conservation of energy, the principle that energy can change form but never be created or lost. The symmetry across directions, the sameness when you rotate your setup, is tied to the conservation of angular momentum, the steady spin that keeps a planet turning. The great conservation laws, energy, momentum, spin, the bedrock rules that everything obeys, are each the shadow of a symmetry. Emmy Noether worked in a time and place that did not welcome her. As a woman in early 20th century Germany, she was barred from holding a proper professorship for years, lecturing at first under a male colleague's name, paid little or nothing. Yet the mathematicians who knew her work, among them the great David Hilbert, recognised its depth at once. Hilbert reportedly argued for her position by saying the university was not a bathhouse, when objections were raised to a woman teaching. Her theorem outlasted every prejudice she faced, and today no physicist can work without it. Once you see physics through symmetry, the whole structure of the laws reorganises around it. The forces themselves, it was gradually understood, arise from particular symmetries, deeper and more abstract than position or time, symmetries in internal properties like electric charge and the colour of quarks. To demand that the laws stay unchanged under these abstract symmetries is to force the forces into existence, to require the photon, the gluons, the carriers of nature's pushes and pulls. Symmetry stopped being a feature of the laws and became their source. This way of thinking did more than organise what was known. It drove the next great unification, the discovery that two of nature's forces, which look entirely different in everyday life, are secretly the same force wearing two faces, joined by a symmetry hidden just out of sight. For most of the 20th century, physicists counted 4 fundamental forces, 4 distinct ways that matter can push and pull. There is gravity, which holds you to the Earth, and the Earth to the Sun. There is electromagnetism, the force of charges and magnets and light. There is the strong force binding quarks into protons and protons into nuclei. And there is the weak force, the most unfamiliar of the 4, the force behind certain kinds of radioactive decay, the force that lets one kind of particle turn into another. 4 forces, seemingly separate, each with its own character and strength. The weak force is strange and easy to overlook, because it does not hold anything together or push anything apart in the way the others do. Its job is transformation. It allows a neutron to turn into a proton, changing a down quark into an up quark and spitting out an electron and a neutrino in the process. This is the root of one kind of radioactivity, and it is also what makes the sun shine, by letting protons convert into the forms needed to fuse and release energy. The weak force is short-ranged and feeble in everyday terms, but without it the sun could not burn and the elements could not have formed. Electromagnetism and the weak force could hardly look more different. One is familiar, long-ranged, the force of a light in electricity, carried by the massless photon. The other is obscure, short-ranged, the force of certain decays, carried by heavy particles. Nothing in their everyday behaviour suggests they are related. Yet in the 1960s, 3 physicists, Sheldon Glashow, Abdus Salam, and Steven Weinberg, working along related lines, showed that these 2 forces are deeply one. At high enough energies, electromagnetism and the weak force merge into a single force, the electroweak force, governed by one symmetry. The reason they look so different in ordinary life comes back to the Higgs field. In the early universe, when everything was searingly hot and energies were enormous, the 2 forces were unified, indistinguishable, a single electroweak force with its symmetry intact. As the universe cooled, the Higgs field settled into place and broke that symmetry. It left the photon massless, so electromagnetism kept its long reach, while it gave great mass to the carriers of the weak force, the W and Z particles, which made the weak force short-ranged and feeble. One force split into two faces as the universe cooled, like a single substance freezing into different forms. The theory made a sharp, testable prediction. It said the weak force must be carried by three specific heavy particles, the W+, the W-, and the Z, and it predicted roughly how heavy they should be, far heavier than a proton. This was a strong claim, and for years the particles were beyond reach. Then, in 1983 at the CERN laboratory, a team led by Carlo Rubbia built the collisions needed to make them, and the W and Z particles appeared, with very nearly the masses the theory had foretold. The electroweak unification was confirmed. Two of the four forces had been shown to be one. This was a quiet triumph, less famous than it deserves, and it pointed toward a tantalizing dream. If two forces could be united, why not more? Perhaps the strong force too joins the electroweak force at still higher energies, all three becoming one. Perhaps at the very highest energies of all, near the beginning of the universe, every force was a single force, and what we see as four is the cooled and broken remnant of that original unity. That dream of total unification drives much of physics still, and it runs into one stubborn, immovable obstacle. The obstacle is gravity. Three of the forces have been brought into the same quantum framework, described in the same language, even partly unified. Gravity refuses to join them. It stands apart, described by a completely different theory, and every attempt to force it into the quantum fold has failed. Gravity is the force you know best, the one that ruled your body from the first moment. It holds you in your chair, pulls rain from the sky, keeps the moon circling the Earth and the Earth circling the Sun. It is the most familiar force of all, and on the scale of planets and stars it is the ruler of the cosmos. So it comes as a surprise that gravity is the one force physics cannot fit into its deepest picture, the one holdout that refuses to be described in the same language as everything else. The trouble begins with how good our theory of gravity already is. In 1915, Einstein gave gravity its modern form in the general theory of relativity. In that theory, gravity is not really a force passed between objects at all. It is the bending of space and time. A heavy object like the Sun warps the space-time around it, and other objects like planets simply follow the straightest available path through that curved space which we see as orbiting. This picture is gorgeous and astonishingly accurate, predicting the bending of starlight, the slowing of clocks near heavy masses, and the ripples called gravitational waves, all confirmed. But general relativity is a smooth theory. It treats space-time as a continuous flowing fabric, bendable to any degree, smooth all the way down with no grain or jitter. The rest of physics, the quantum world of particles and forces, is built on the opposite idea. There everything comes in discrete packets, everything jitters with the restless uncertainty of the quantum, nothing is perfectly smooth. The other three forces are quantum forces, carried by particles humming with vacuum fluctuations. Gravity, as Einstein wrote it, is smooth and classical, with none of that quantum trembling. To unite gravity with the rest, physicists need a quantum theory of gravity, a version in which gravity too comes in packets and jitters like everything else. There should be a particle that carries gravity, by analogy with the photon and the gluons, and it even has a name, the graviton, though it has never been seen. The problem is that when physicists try to write the quantum theory of gravity the same way they wrote the others, the mathematics falls apart. The calculations produce infinities, nonsensical answers, quantities that blow up to infinity instead of giving sensible numbers. The methods that tamed the other forces simply break. The root of the breakdown is that gravity, at the smallest scales, becomes violent in a way the other forces do not. Quantum theory says that at tiny enough distances, the vacuum churns ever more wildly, with more and more energy packed into smaller spaces. For the other forces, this is manageable, but energy is the source of gravity, so wilder fluctuations mean wilder gravity, and at the smaller scales the churning space-time tears itself into nonsense in the equations. The very fabric that general relativity treats as smooth would, under quantum rules, boil into a froth no one can describe. So we're left with two magnificent theories that do not speak to each other. General relativity governs the large and the heavy, planets, stars, galaxies, the whole universe, with perfect accuracy. Quantum theory governs the small and the light, particles, atoms, forces, equally well. Almost always these two domains stay apart, the large and the small, and each theory rules its own and never meets the other. The conflict stays hidden because the situations where both matter at once are so extreme. But those situations exist, and they are not idle. At the centre of a black hole, and at the very first instant of the universe, matter is both unimaginably heavy and unimaginably small, so both theories apply at once, and they contradict each other. There, our physics gives no answer. To describe the heart of a black hole or the birth of everything, we would need the quantum theory of gravity we do not have, and part of what makes that theory so hard is a puzzle about why gravity is so strangely, absurdly weak. Here is something you can feel for yourself, though you never think of it this way. Hold a small magnet over a paperclip on a table, and the magnet lifts the clip. In that moment, a tiny magnet, something you can hold between two fingers, overpowers the gravity of the entire Earth, the whole planet pulling down on that clip, beaten by a scrap of metal. The electromagnetic force in the little magnet wins against the gravity of a world. That contest, so lopsided you never notice it as a contest, hides one of the strangest facts in physics. Gravity is fantastically, almost unbelievably weak compared to the other forces. We do not feel it as weak, because we live next to the Earth, an enormous mass whose pull adds up to something we cannot ignore. But measured between individual particles, force against force, gravity is feeble beyond easy description. The electric force between two protons is stronger than the gravitational force between them by a number with about 36 zeros in it. Gravity, the force that shapes galaxies, is by far the weakest of the four, and not by a little, but by an almost incomprehensible margin. This enormous gap in strength is called the hierarchy problem, and it is one of the deepest puzzles in physics. The forces line up in a vast ladder of strengths. The strong force is the most powerful. Electromagnetism is weaker, the weak force weaker still, and then, far below all of them, separated by an immense empty gulf, sits gravity, almost nothing by comparison. The question is why? Why should gravity be so absurdly far below the others? What sets that gigantic gap? And why is there such a desert of emptiness between gravity and everything else? The puzzle grows sharper when you bring in the Higgs. The mass of the Higgs particle, measured at the Large Hadron Collider, turns out to be far smaller than the natural calculations suggest it should be. The quantum churning of the vacuum should, by the ordinary logic of the theory, drag the Higgs mass up to an enormous value, close to the scale where gravity finally becomes strong. Instead, the Higgs sits light, almost delicately so, as though some precise cancellation were holding it down, trimming away a huge number to leave a tiny remainder. Nothing in the standard model explains why that cancellation should happen. For decades, physicists hoped a beautiful idea called supersymmetry would solve this. Supersymmetry proposed that every known particle has a heavier partner, a whole shadow set of particles, and the effects of these partners would naturally cancel the dangerous contributions and keep the Higgs light. It was elegant. It tied together loose ends, and many were confident the Large Hadron Collider would find these partner particles. The collider looked hard at energies where the simplest version said the partners should appear. So far, it has found nothing. The partners have not shown up where they were expected, and the elegant solution is in trouble. So the hierarchy problem stands open and uncomfortable. Either there is some mechanism we have not yet found that keeps gravity weak and the Higgs light, or the values are simply what they are, finely balanced for no reason we can name. Some physicists have turned to a more unsettling thought. that the value is not explained by any principle, but selected by the bare fact that we are here, since a universe with different settings would have no galaxies and no observers. That idea troubles many, because it trades a mechanism for an accident. These open wounds, the unexplained numbers, the weakness of gravity, the gap that swallows it, all hint that the standard model is not the bottom. Something lies beneath it, some deeper layer where these arbitrary facts might finally have reasons. And so physicists keep asking the oldest question of this whole descent, whether the pieces we call fundamental are truly the end, or whether they too have an inside. We have reached the particles the standard model calls fundamental, the ones with no known parts, the electron and the quarks and the rest. But we've been here before, at what looked like the bottom, only to find another floor below. The atom was fundamental until it held a nucleus and electrons. The proton was fundamental until it held quarks. So it's only natural to ask the same question one more time. Are the quarks and the electron truly the end, or do they too have an inside, a still smaller layer waiting to be found? The pattern of history makes the question hard to dismiss. Every time we built a tool sharp enough to look closer, the supposedly indivisible piece opened up. And there are hints in the standard model itself that whisper of deeper structure. The 3 generations, those repeating copies of matter, look suspiciously like a pattern, and patterns in physics have usually meant underlying pieces, the way the rows of the periodic table meant protons and neutrons underneath. Perhaps the quarks and leptons of the 3 generations are not fundamental, but are themselves built from a smaller set of pieces, combined in different ways to give the different particles. Physicists gave these hypothetical smaller pieces a name, preons, the parts that would lie inside quarks and electrons. The idea is appealing for the same reason the quark idea was appealing. Just as a handful of quarks explain the crowded particle zoo, a handful of preons might explain the dozen matter particles in their 3 generations, collapsing them into combinations of something simpler. The up quark would be one arrangement of preons, the electron another, and the whole table would fall out of a few deeper ingredients. It would be the next rung down the same ladder we have been climbing all along. But here, for the first time, the ladder seems to stop, or at least to hide its next rung very well. Despite the appeal of the preon idea, there is no evidence for it. None at all. The experiments that smashed protons hard enough to reveal quarks have smashed electrons and quarks far harder still, probing them at scales thousands of times smaller, and they continue to behave as perfect points, with no inside, no sign of structure, no hint of smaller pieces within. As far as the most powerful experiments can see, the electron is exactly what it appears to be, a true point with no parts. There is also a deep theoretical obstacle that makes preons hard to build. If you try to confine smaller pieces inside something as light as an electron, the uncertainty principle works against you. Squeezing pieces into a tiny space gives them enormous energy of motion, and by the link between energy and mass, that should make the resulting particle very heavy, far heavier than the electron actually is. The electron is too light to comfortably hold pieces inside it. Making preons work means getting around this problem, and no one has found a convincing way to do it. So the descent reaches a strange and honest pause. The electron and the quarks might be truly fundamental, the actual bottom of the ladder of matter, the first things in all our digging that have no inside. Or there might be preons, or some other deeper layer, hidden at scales we cannot yet reach, waiting for a sharper tool than any we have built. We do not know which. For now, the matter particles stand as points, indivisible as far as we can see, and the question of whether they have an inside has no answer. If the descent through smaller and smaller pieces of matter has reached its limit, that does not mean the deepest layer is empty. Some physicists believe the bottom is not a particle at all, not a point of matter, but something else entirely, a tiny vibrating thread whose music makes every particle we know. For most of this descent, we have imagined the fundamental pieces as points, the electron and the quark as objects with no size at all, mathematical points carrying mass and charge. That picture works, but it carries hidden troubles. A point of zero size with charge packed into it leads to infinities in the equations, the same kind of blow-up that wrecks attempts at quantum gravity. So some physicists asked whether the bottom layer might not be points at all, but something with a tiny bit of extension, the smallest possible objects that are not points. The answer they reached for was strings. String theory proposes that if you could look closely enough far below the scale of any experiment, you would find that each particle is not a point but a tiny vibrating thread, a string. These strings are unimaginably small, so small that at the scales we can probe they look exactly like points, which is why we have never seen their extension. Each string can vibrate like the string of a guitar or a violin, and the way it vibrates determines what particle it appears to be. One pattern of vibration looks like an electron, another looks like a quark, another looks like a photon. The image at the heart of the theory is genuinely beautiful and worth holding for a moment. A guitar string, plucked different ways, plays different notes, and the notes are all the same string vibrating in different patterns. String theory says the particles are like that. The electron, the quark, the photon, every piece of matter and every carrier of force would all be one kind of thing, a string playing different notes. The bewildering variety of particles would become a kind of music, a spectrum of vibrations on the same underlying thread. All the matter in the universe would be harmonies of a single instrument. String theory's great promise is that it seems to include gravity naturally, which no other approach manages so cleanly. Among the notes a string can play, one matches the long-sought graviton, the particle that would carry gravity in a quantum theory. Gravity, the force that refused to join the others, falls out of string theory on its own, without being forced in. For this reason, many physicists have seen string theory as the most promising path to the dream of unification, a single framework holding all the particles and all four forces, gravity included, as different songs of vibrating strings. But string theory asks for things that are very hard to accept and very hard to test. For the mathematics to work, the strings must vibrate not in the 3 dimensions of space we know, but in many more, around 10 or 11 dimensions in total. The extra dimensions, the theory says, are curled up so small that we never notice them, hidden at every point in space. And the strings themselves are so fantastically tiny that no machine we could imagine building could ever resolve them directly. The scale of a string is so far below what any collider can reach that the theory's central objects may be forever out of direct sight. This is the hard problem with string theory, and it divides physicists deeply. The theory is mathematically rich, and has reshaped parts of physics and mathematics along the way. But after decades of work, it has made no clear prediction that an experiment can check, no number we can measure to confirm or refute it. Some see it as the deepest description of nature we have, waiting for the means to test it. Others worry it has drifted away from the discipline of evidence that has guided physics all along. It might be the bottom of the world, or a beautiful structure built on air, and for now we cannot tell which. String theory is not the only attempt to reach the deepest layer. Another approach leaves the particles alone, and asks instead whether space itself, the stage everything plays on, might be the thing that comes in pieces. Every theory we have met so far has treated space as a smooth backdrop, a continuous stage on which particles and fields play out their story. You can move any distance you like, however small, and space simply continues, infinitely divisible, smooth all the way down. Even quantum field theory, for all its jitter, sets its restless fields on a smooth, continuous space. But there is a different idea, a rival approach to quantum gravity, that questions this. It asks whether space itself is smooth, or whether it too, like matter and energy, comes in the smallest possible pieces. This approach is called loop quantum gravity, and it takes a very different path from string theory. Rather than starting with tiny vibrating threads in many dimensions, it starts with space and time themselves and asks what they are made of at the deepest level. Its answer is that space is not a smooth continuum but a fine weave, a network of tiny loops linked together and that what we experience as smooth space is really this network seen from far away. Space, in this picture, has a grain, a finest possible texture, below which the very idea of distance stops making sense. The image to hold is one you already know from everyday things. Look at a photograph in a newspaper from across the room, and it seems a smooth image, continuous shades of grey. Bring it close and you see it is made of tiny separate dots, with nothing between them. The smoothness was an illusion of distance. Loop quantum gravity says space is like that. At the scales we live at, it looks perfectly smooth and continuous. But if you could look closely enough far below the size of any particle, you would find it is woven from discrete pieces, finite chunks of volume linked in a network, with no smaller distance possible. In this theory, space comes in smallest possible units of volume, and area comes in smallest possible units too. There is a tiniest chunk of space, an atom of space in a sense, below which there is no smaller volume, just as matter has its smallest pieces. The smooth space of our experience is built from countless such chunks, woven together into the network the theory describes. Even time in some versions becomes grainy, advancing in smallest possible steps rather than flowing continuously. The continuous stage dissolves into a fine, discrete fabric. Loop quantum gravity has a different strength from string theory and a different weakness. Its strength is that it takes Einstein's picture of gravity as curved space-time seriously and tries to make that very space-time quantum, granular, without bolting on extra dimensions or unseen partners. It aims squarely at the thing general relativity describes and tries to find its atoms. Its weakness is the mirror of string theories. Where string theory naturally includes the other forces and particles but struggles to connect to experiment, loop quantum gravity focuses on space and gravity, but does not naturally bring in the particles of the standard model, the matter and forces we actually see. Like string theory, loop quantum gravity is fiendishly hard to test, because the graininess it predicts lies at a scale so impossibly small that no experiment we have can reach it. Both theories point to the same forbidding frontier, the same unimaginably tiny scale where smooth space and ordinary physics are supposed to give way. Whether the deepest layer is vibrating strings, or a woven network of space, or something no one has yet imagined, they agree that the change happens down at one particular size, the smallest length that physics still considers meaningful. It is worth asking what that smallest length actually is, and why nature seems to have a flaw at all. Through this whole descent we have been going smaller, from the table to the atom to the nucleus to the quark, each step a leap down in size. A natural question is whether this can go on forever. Can you always go smaller, halving the distance again and again without end, or is there a smallest meaningful length, a flaw to the world below which the very idea of distance falls apart? Modern physics suggests there is such a flaw, and it has a definite size, almost unimaginably small. That smallest meaningful length is called the Planck length, named after Max Planck, one of the founders of quantum physics. It is not small in any ordinary sense. It is small in a way that defeats comparison. To get a feeling for it, take the size of a proton, already 100,000 times smaller than an atom. The Planck length is smaller than the proton by about as much as the proton is smaller than the distance from here to a nearby star. You step down from the proton by that vast factor, and only then do you reach the Planck length. It sits far below anything any experiment has ever touched or likely ever will. What makes this length special is not just its size, but what happens there, where the two great theories finally collide head-on. The Planck length is the scale at which quantum uncertainty and gravity become equally important at once, where the smooth space-time of general relativity and the restless jitter of quantum theory can no longer be kept apart. Above this scale, you can use one theory or the other and stay safe. At the Planck length, you would need both at the same time, the quantum theory of gravity we do not have. It is the doorway past which our physics simply stops giving answers. At that scale, the smooth picture of space is expected to break down completely. The quantum churning of the vacuum, mild at ordinary scales, would grow so violent at the Planck length that space-time itself would boil, frothing and tearing in ways no current theory can describe. The very notions of distance and time, of here and there, before and after, may lose their meaning in that froth. To ask what happens at a distance smaller than the Planck length may be like asking what lies north of the North Pole, a question that sounds sensible but has no answer, because the idea behind it gives out. This is why the Planck length is often called the floor of the world. It is not that we lack a fine enough ruler to measure below it, though we do. It is that the concept of a smaller distance may not mean anything at all. Length itself may bottom out here. Both string theory and loop quantum gravity place their deepest structures right around this scale, the strings vibrating at roughly the Planck length, the woven chunks of space sized near it. Different as the theories are, they agree that something fundamental changes at this smallest length, that this is where the ordinary world ends. So the descent that began with your hand on a solid table reaches at last a possible bottom, a smallest meaningful size built into the structure of reality. Below the table, the atom. Below the atom, the nucleus and the electron. Below the proton, the quarks. Below the quarks, perhaps strings or woven space, and below all of it, the Planck length, where distance itself runs out. Whether this is truly the bottom or just the limit of our sight, we cannot yet say. But even if the standard model and these deeper ideas were complete, there would still be enormous things they fail to explain, sitting in plain view all around us. Suppose we set aside the deepest questions, the strings and the woven space and the Planck length, and ask only whether the standard model, our tested and confirmed theory, explains the universe we actually see. It does not, and not by a little. The matter described by the standard model, every particle in its catalogue, all the quarks and leptons and force carriers, adds up to only a small fraction of what the universe is made of. Most of the cosmos is something else, something the standard model says nothing about. When astronomers measure how galaxies spin, they find a problem. The stars at the edges of galaxies move far too fast. With only the matter we can see, the visible stars and gas, gravity would be too weak to hold those fast-moving stars in, and the galaxies would fly apart. Yet they hold together. Something unseen is there, adding gravity, holding the galaxies in shape. Physicists call it dark matter, and there is about 5 times as much of it as all the ordinary matter in the universe. It does not shine, does not absorb light, does not appear in any form the standard model can name. We feel its gravity and nothing else. Dark matter is not a small correction. It outweighs everything in the standard model's catalogue by 5 to 1. Whatever it is the main material of the universe, the unseen scaffolding on which galaxies are built, and our best theory of particles has no place for it. Some new kind of particle, never yet detected, may make it up, and experiments have hunted for such particles for decades, deep underground, in great sensitive detectors. They have found nothing definite so far. The most common substance in the cosmos remains entirely outside our theory of matter, and dark matter is only part of what the standard model misses. There is a darker mystery still, called dark energy, a strange pressure that is pushing the universe apart, making its expansion speed up over time. Dark energy is even more abundant than dark matter, making up most of the total content of the universe, and its nature is even less understood. Between dark energy and dark matter, the ordinary matter we and our theory know is left as a thin sliver of the whole, a few % of everything, with the vast majority unexplained. Even within ordinary matter, the standard model has a crack it did not predict. The theory in its original form said neutrinos should have no mass at all, should be perfectly weightless, like the photon. But experiments found that neutrinos change from one type to another as they travel, flickering between the 3 kinds as they fly across space, and this changing is only possible if neutrinos have a small mass after all. They are not weightless. The discovery, confirmed around the turn of this century, showed the standard model was wrong on this point, and where the neutrino's tiny mass comes from is still not fully understood, So our finest theory of matter, for all its precision, sits in a universe it cannot fully account for. It describes the thin sliver of ordinary matter beautifully, predicting experiment after experiment to many decimal places. But it is silent on dark matter, the larger share of the material universe. It is silent on dark energy, the largest share of all. And it was wrong about the neutrino's mass, a sign that even within its own territory the theory is not finished. The holes are not at the obscure edges, they are most of the universe. These gaps are real and serious, and physicists feel them keenly. But there is one mismatch worse than all of these. A single prediction the theory gets so spectacularly wrong that it stands as the largest error in the history of physics, and it comes back to the seething vacuum we met before. Remember the vacuum, the empty space that is not empty, seething with virtual particles flickering in and out, jittering with its restless zero-point energy. That activity is real, confirmed by the Lamb shift and the Casimir force. The empty space around you genuinely hums with energy. Now ask a simple question. How much energy? If the vacuum is full of this restless activity, that activity should have a total amount, an energy packed into every cubic inch of empty space, and that energy should have an effect on the universe as a whole. The effect would be gravitational. Energy, by Einstein's relation, has mass, and mass gravitates, so the energy of empty space should pull on the universe, or push on it, shaping how the cosmos expands. The energy of the vacuum should act on the larger scale of all, bending the expansion of space itself. So there are two ways to get at the vacuum energy. You can calculate it from quantum theory, adding up the restless activity of all the fields, and you can measure its actual gravitational effect on the expanding universe. Both can be done, and the two numbers should agree. They do not agree. They miss each other by the widest margin in the history of science. When physicists calculate the energy of the vacuum from quantum theory, adding up the jitter of the fields, they get an enormous number of vast energy packed into every scrap of space. When they measure the actual energy driving the universe's expansion, they get a tiny number, almost but not quite zero. The two differ by a factor so large it is hard to write in words, a 1 followed by some 120 zeros. The prediction overshoots the measurement by that staggering amount. This is often called the worst prediction in all of physics, and the title is well earned. A factor of 120 zeros is not a near miss or a modest error. It is the most spectacular failure of a serious calculation that physics has ever produced. Our theory of the vacuum, which gets the Lamb shift and the Casimir force exactly right, which works to many decimals on small scales, gives an answer for the total vacuum energy that is wrong by more than any quantity has ever been wrong in the whole of science. Something is deeply, profoundly misunderstood. The strangeness deepens when you look at the measured value, the real energy of empty space. It is not zero, which might be explained by some unknown principle that cancels the vacuum energy out completely. It is a tiny positive number, almost zero but not quite, finely poised just above nothing. This faint residue is the dark energy from before, the gentle pressure pushing the universe to expand faster. So the vacuum energy is real and it matters. It is the very thing accelerating the cosmos, but its size is 120 zeros smaller than our theory says it should be, and no one knows why. This single mismatch may be the largest clue we have that something fundamental is missing from physics. It sits at the exact meeting point of the very small and the very large, where the quantum vacuum meets the expanding universe, precisely the place where our two great theories already refuse to join. The worst prediction in physics is not a small embarrassment to be patched. It is a signpost, pointing at a gap in our understanding so deep that filling it may require a new picture of the vacuum, of gravity, and of the universe all at once. And so the long descent ends not in a tidy floor but in open questions, in a vacuum we cannot account for, and a universe mostly made of things we cannot name. It is time to climb back up, to your hand on the table, and ask what all of this has shown. Put your hand back on the table. It still feels solid, still cool, still completely there, and it still holds your weight without giving an inch. Nothing about the feeling has changed. But you know now what is underneath it, and the knowing changes what the feeling means. The solidity is real, but it is not made of solid stuff. It is force reaching across emptiness, the electron fields in your skin pressing against the electron fields in the wood, a standoff held a hair's breadth above true contact. Follow it down, and the descent is clear in memory now. The table is built of atoms, and each atom is almost entirely empty space. A tiny dense nucleus with a thin cloud of electrons far out around it. The nucleus is protons and neutrons, packed impossibly tight. Each proton is 3 quarks in a storm of gluons, and almost all its weight is the energy of that storm, not the quarks themselves. The quarks and the electron are ripples in fields that fill all of space, and even the empty space between them seethes with borrowed particles flickering in and out. That is what your hand is resting on, all the way down. So we can answer the question we started with, the one that is easy to ask. What is everything made of, all the way down? The honest answer has 2 parts. As far down as we have been able to see, everything is made of a small handful of fundamental particles, a few quarks and leptons and force carriers, better described as vibrations in fields than as tiny balls. That much we know, and we know it with breathtaking precision, confirmed by a century of experiment. It is one of the great achievements of our species, this map of the bottom of the world. The second part of the answer is the harder and more honest one. We do not know if that is really the bottom. Below the particles may lie strings, or woven grains of space, or preons, or something no one has yet dreamed, hidden down near the Planck length where distance itself runs out, and our theories fall silent. And even at the level we do understand, the questions crowd in. We cannot say why there are 3 generations of matter, why the particles have the masses they do, why gravity is so absurdly weak, what most of the universe is made of, or why the energy of empty space is so far from what our theory predicts. The descent ends in a ring of open questions. There is a particular kind of wonder in that ending, and it is worth naming plainly. We have looked further into the small than any people before us, far enough to find the genuine edges of human knowledge, the places where the map gives out. The hidden layer beneath the atom is partly charted and partly blank, and the blank parts are not failures but frontiers, the open questions that the physics of this title promised and could not fully answer, because no one yet can. To know exactly where understanding stops is itself a hard-won kind of understanding. And here is the last thing, the thing to carry away from the table. You are made of this. Your body is atoms that are mostly empty, nuclei bound by the leaked edge of a deeper force, protons whose weight is mostly energy. All of it ripples in fields that fill a seething vacuum, shot through with the same open mysteries that haunt the largest questions in science. The unexplained numbers run through you. The unsolved vacuum is the space inside you. You're not separate from the deep strangeness of the universe, watching it from outside. You're made of it, all the way down, and tonight you have followed yourself nearly to the bottom and seen how far the light still reaches, and where it does not.